Welcome to our discussion of a brief history of programming languages. With this presentation, I hope to give you just a brief perspective on how programming languages have evolved over time. As we look at programming languages, keep in mind that there are four parts to any basic computer. Now, this is typically called the von Neumann architecture. There's a central processing unit, which includes three main pieces: a program control unit, which is responsible for interpreting instructions and providing setup; the arithmetic logic unit, which actually executes the instructions; and registers, which are small amounts of memory for temporary storage and such things as error flags. So beyond the CPU, there's also a main memory, which we typically call RAM these days, input devices, and output devices. All of these items are connected and communicate via a bus. If you have these pieces, you have a basic computational device. Graphically, we can display the von Neumann architecture kind of like this. Now, the first languages, when it comes to digital computers anyway, are machine languages. These are simply binary numbers, or we can think of them that way. Simply used to identify memory locations, denote CPU registers, and ultimately to represent instructions. Now, machine languages still exist today, though you don't often hear much about them. They're still there. We've created higher level languages which we use to actually communicate instructions, but ultimately those higher level language instructions like C++ have to be translated to machine language. They're very difficult to learn and even harder to use. When you hear about a CPU these days, sometimes you hear about the instruction set for a CPU, which is sometimes called the machine instruction set. Every CPU has a built-in set of operations it can understand. Those operations are fundamentally in machine language. Some common machine instructions that you hear about in any computer are things like this. Things like data movement operations. For example, moving data from one place in memory to another. Moving data back and forth between memory and the CPU. Performing simple input and output, and simple math operations. Take a moment to review this list before moving on. Machine languages are very difficult to use, so over time it was decided that something else should be tried. The next level was assembly language. These are symbolic programming languages which mimic the structure and organization of machine languages but replace binary code with sets of mnemonic symbols. It's still difficult to learn, but it is a bit easier to read the machine code, and it's still used today. We use a special software program called an assembler to translate our assembly language into machine code. The unfortunate part of assembly languages is that they are processor specific and they're still very primitive. There's an example of assembly language here in the lower right. Here's another example of assembly language, and this is actually a program I wrote in college. Very simple program which doesn't do a whole lot, but uses things like the registers. AX, BX, CX, and DX, if you can locate them in the code, all represent registers on an Intel CPU. It's just a matter of moving data into registers and then using what's called a stack to actually store some data temporarily and to get the computer to do a few things. Well, after assembly languages, they said there has to be something better. So they came up with what's called high-level languages, and this is the type of thing we use today. They said, well, we can create more complex symbolic representations. Now, a couple languages come to mind when it comes to the first high-level languages. One is Fortran, which stands for Formula Translation. This was the first real high-level programming language. In 1958, we saw the first working compilers, and it's still used today in the scientific community and elsewhere. It's designed mainly for scientific applications, and the goal was to be able to use mathematical notation as well as provide fast and efficient machine language code. Now, one big advantage of high-level languages is that you could take them after you've written the programs and move them from one computer to another. As long as you had a compiler for that specific machine, it would do the translation. Now, this is in theory what should happen, but of course there are some bumps along the way here and there. So Fortran allowed people to do simple statements such as an assignment statement, x equals 2, for example, and to do more complex mathematical expressions using the algebraic syntax that we're used to. Now, this was a great leap forward because it shortened the amount of code you had to write as long as you had a working compiler that could translate it into machine code. But it also introduced concepts that we come to take for granted today, such as comments, do loops, or what you might call while loops, I/O formatting, and subroutines, what you may call functions. Now, here's an example of Fortran code. Take a moment and just absorb it here. Take a look at how it differs from what you may have used in C++ or another language. Now, this is older Fortran. This is written in Fortran 77, as we call it. Some things have changed over time, but generally speaking, it adheres to today's syntax. You notice you have write and read, which are the I/O facilities. You have variable declarations at the top with types like integer times 4, which means a 4-byte integer, character, and logical, which is what you might call a bool variable from C++. But you'll also notice things like an if statement, something that we're used to from C++ and other languages. Some other landmark high-level languages that you may or may not have heard of. Number one is ALGOL. ALGOL has a long history in the sense that we've had a lot of derivative languages which we still use today. It was the first what we call block-structured language, and the first language to have integrated if and for statements. Now, by block-structured, the way you can think of that now is that in C++ you have blocks. Now, what that is sets of code delimited by curly braces. That's a block. Well, ALGOL was the first block-structured language. Now, C was developed in 1969 at Bell Labs. It's the language of Unix and Linux and the predecessor of C++. It's still heavily used today. It's very fast, very efficient, and is used for a variety of different things, from operating systems to embedded systems, you name it. Now, Pascal, you may not have heard of. It was developed in the early 1970s. It was really a teaching language. It was what I had when I was a computer science undergraduate for the first really 2 years. Now, it was very easy to learn. As a result, that's why they wanted to use it to teach programming, but it was limited. But by the mid-1980s, Pascal was the predominant language taught in universities. By the mid-90s, it had been replaced by C++, which eventually got replaced by Java and is now being replaced by Python. Now, here's an example of Pascal code. Now, if you look at some of the code here, you'll see some things that you see in other languages. There's a while loop. There's an if statement. There's a cascading if, or an if-else-if statement. There's assignment statements, putting data into variables. Now, a curious thing about Pascal is that comments look a little bit different. Comments in Pascal are surrounded in curly braces. Now, think about that and how it's used differently in C++. We use curly braces to group statements together into blocks. Some other notable languages you may have heard of are listed here. Of course, C++, which you may have had in IST 140, really just a refinement of C with some object-oriented programming thrown in, which you normally don't get to in IST 140, but you may have seen. Ada is another notable language from created in the early 80s, championed by the Department of Defense, is an object-oriented language that was heavily used and still is used in many different sectors, especially science. Visual Basic came around in the early 90s, as did Python. Java in the mid-90s, intended to be a cross-platform language. We'll learn a little bit more about Java here starting next week. JavaScript, no relation to Java. PHP, also in the mid-90s. And in 2001, C#. So how did programming languages evolve in terms of their use? Well, early on, Fortran was looked at as something that could be used for a variety of different things, mainly scientific applications. However, its use in business was kind of limited. Many of the people working on computer systems in business had no formal training in programming or mathematics, so they wanted something that was a bit more readable, a bit more, shall we say, flexible, and a bit more oriented toward what they needed to do, which was data and file processing. So COBOL was devised, again in the late 1950s. Now, the syntax of COBOL is very verbose and it's very English-like. The lady on the right is Admiral Grace Hopper, and she's often thought of as the mother or grandmother of COBOL, having come up with some of the early ideas for the language. Now, here's an example of COBOL code. You'll notice it is very wordy. The statements are very English-like. For example, write report line from total records line after advancing 2 lines. Obviously, this particular little subroutine here is intended to do a portion of a report that's being printed. Now, you will see common elements, like there's an if statement here. It's using a file, so you see things like close the file. You see write, which is the output mechanism. But it is very verbose, and as a result, computer scientists typically don't like this language. So beyond business use, programming languages have evolved in terms of their use in systems programming. These are people who work on operating systems and compilers. Systems programmers are worried more about things like efficiency. Especially with embedded systems, you often don't have a lot of memory, so you have to be very efficient in how you use that memory. Now, to give you an example from popular culture, one of the first home video game systems that was very popular was the Atari 2600. Well, there was only 4K of memory available for those games. So people who programmed for the Atari 2600 had to be very creative and very frugal with how they used that memory. There were some other limitations they had to adhere to as well to make the games actually do something that people would enjoy. Now, the problem with high-level languages early on was they lacked some of the low-level features and the speed that machine languages and assembly languages would provide. Now, C was the one that really broke that barrier. Fortran over time was getting much faster and doing a good job, but C was one that included the low-level features like bit manipulation. You can actually do that in C and C++, as well as many of the benefits of higher-level languages, such as the ease of writing expressions and things like that. The disadvantage of many of the languages used for systems programming has often been readability and the I/O facilities. C's I/O facilities are notoriously cryptic, and if you wanted to write something very confusing in C, you could fairly easily. Now, over time, as programming became more an integral part of business and organizations, modularity became an issue. As engineering kind of crept its influence over the systems development process, because of the way that the programs grew, it was decided that, okay, we have a lot of code here, we need to organize it in some way. So it was decided that programs needed to be organized as a set of what we call independent modules, things that could be plugged together with other code as needed to form larger and larger systems. This idea of creating modules that had what's called a public interface is something we're going to return to here when we get into Java in a few weeks. Now, the implementation details will be hidden inside the module itself. Now, this is really the beginnings of the thoughts of, well, write code once, use it many times. Don't reinvent the wheel, just simply pull something off the shelf, plug it into what you need, and be able to use it. And that was really the goal. Reuse, something you'll hear again and again. Now, there are two important aspects to modularity. One is the physical decomposition of a program into separate and independent modules. That's just simply taking the code and separating it. Now, the logical decomposition is more of an abstract idea. This is the ability of the programmer to work at a high level of abstraction during the design phase, to be able to think about a large system in terms of pieces and logical pieces that could snap together. Not just the low-level minutia of the code, but thinking at a higher level. Now, in implementation, modularity kind of got its push through things like functions and subroutines. Now, functions and subroutines are more or less the same thing. Now, when we talk about modularity, we're talking more or less about object-oriented programming, something we're going to get into in this course. So here are some key terms to remember. You should know what von Neumann architecture is and the different components. You should know what a machine language is. You should know what a machine instruction set is, an assembly language, high-level languages. Languages like Fortran, Algol, COBOL, Pascal, and C, you should know, well, what are they for? What were their roles? You should know what systems programming generally is, and you should understand the concept of modularity.